Hello, my name is Scott Mesjin, and today I'll be going over the first problem for week 8's explainer videos. Um, so let's get into it. Here's the document where you'll be looking at the problems, and then I made my own to go over the solutions. So the first part is the problem setup. In this part, we're tasked with, I believe it is just finding the Q. Yeah, so we're just trying to find the Q, and just note in the problem they express Q as a little q or lowercase q. So we'll be substituting lowercase q for this Q into the gas. Yeah, and it wants us to express it in terms of V, delta V, and T. Um, what I found is that the best I could get was in this form. So yeah, that's just kind of what I went with. But anyways, the first thing I found was that you can also write this given form as um, negative work by the gas. And we do that because the signs work out later. So yeah, you'll see that. Also, I have just some basic equations here. So um, here's work that we'll need, volume of the cylinder. So um, obviously there's a pi r squared is the area, and then just h is like the height of the cylinder. And so when we have this change in volume, um, it kind of just corresponds to the change in height because there's not really a change in area. Um, yeah, so here I have that we start with E thermal is equal to negative work plus Q. And then I substitute in temperature for E thermal and work for uh, force and change in distance. And then I also substitute in little q because that's what the problem is asking for. Um, so then that's here. In this next part, I just move the force and change in distance to the other side. And then for force, you may recall that force is equal to just a pressure over an area. So in this case, the area that we're working with is just pi r squared because that's the area that's being moved. Um, so yeah, like the lid of this would be moved, not like, yeah, if that makes sense. So yeah, that's what we substitute in for um, the force, and that'll be here. And then we also substitute in distance for change in distance for change in height, because that's what's really changing in this problem. And then also note that change of height is equal to this equation when you solve for change in height in this equation. Um, so yeah, once we do that and rewrite it, then we get the final answer that is um, equal to what we're supposed to get. So that's good. Q is equal to temperature plus density delta V. So now it asks how many microstates are there? Um, and it also specifically asks in this question, why does the number of microstates scale like volume to the squiggly n power? Um, so my explanation for this was that say there were squiggly n is equal to 0, right? So that would mean that the number of uh, like particles would be 0. So if there's no particles, then you would plug into this equation, right? And anything to the 0 power is 1. So you'd only have one microstate, and that'd just be the empty microstate, right? Where there's nothing happening, there's just a volume, no particles. For where there's one particle, there are as many, this should say volume, there are as many microstates as the volume permits because it could be, here, 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 anywhere in the volume. It just has to be in that space. And then, so that would mean that it would make sense for the uh, amount of microstates to scale with the volume, with the power to the volume, because as you're adding more particles, there just becomes a lot more possible microstates. Um, because you have the potential for particle to be here and here if there's two, and then also like here and here, or just swapped like it yeah, there's a lot, and you know, as that goes up to infinity, there's uh, a ridiculous amount of microstates. Um, for 1.3, the ratio of microstates after versus before the expansion. For this part, our task is to prove that this expression can be simplified to this expression, and it shows you some little steps along the way to make sure you're getting there right. And then for this problem, it also tells you that you can approximate this expression to be equal to x for small x, and then also you will need to use this substitution. K Boltzmann is equal to the R constant over Avogadro's number. So first things first, we can start by substituting in the n init with this expression on the bottom, volume to the squiggly n power, because of this expression. From there, we know that in the final number of states, that is dependent on the previous volume as well as the change. So that's why we substitute in v plus delta v, and then that is also to the squiggly n power. And from here, we use a magical log property, as I've written, to basically take out the exponents and put them in the front of the log. From there, you can divide both v and delta v by v to get 1 plus delta v over v. From there, you apply the small x property up here because delta v is a small number, so a small number over a big number would be less than 1 and almost 0. So that would be a very small x. From there, you get this, and then substituting in a form of PV equals nRT, we get this equation. And then right here is a little bit complicated of a step. So I write here that delta V is equal to Q over P. And this is because of our previous equation where we have Q is equal to T plus density change in volume. And we can do this because the question says it's isothermal. So then T is equal to 0. Yeah, so then we get essentially no T here, and we rewrite this in terms of delta V to get here. And then after that, we use this equation that we got from 1.2, and we rewrite it in terms of Avogadro's number, and then we get here, and then you use the K Boltzmann, but use the inverse of it more specifically, and then you get to the final step. So nice, we got there. It took a lot of substitutions, but you get there. And then for the last step, proving entropy, our task is to prove that delta S is equal to Q over T. And it shows that we're going to have to make this substitution. So you just start by making that substitution in the final and initial. So then you have nfen and ninit in these logs. And now we can apply a magical log property yet again. So remember that nfin over ninit inside a log could be simplified to the subtraction of them. So you could do the opposite and go backwards to make the log look like this. And then after that, we get to this point. And remember that we already solved this part of the equation in 1.3. And we got this as our final answer. So we'll just go ahead and substitute this in. So once we do that, we get K Boltzmann times Q over K Boltzmann times T. K Boltzmanns cancel out, and you're left with Q equals T, which is exactly what we wanted. So yay. That's thank you. Hope that was helpful.